Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the fourth part of Chapter 7, the constraint qualification. We will basically introduce the following definitions to derive the constraint qualification. One is tangent cone, another one is linearized feasible direction, and finally the linearly independent constraint qualification. Now, let's start with a brief talk about constraint qualification. As we analyzed in the previous parts for first-order optimality condition, we have derived the first-order optimality condition by using some sort of linear expansion, okay? And then we get the mathematical form for first-order optimality condition. However, a question is whether such linear approximation works or whether it is sound. So we have to provide some theoretical investigation to prove this. And this theoretical tool is just the constraint qualification. In other words, the constraint qualification actually shows that under what condition we can do linear expansion to the constraints as well as to the function values. Okay. Now let's first take a look at the tangent cone. We start with the definition about a feasible sequence approaching a point x. So assume that omega is a closed convex set, and we given a feasible point x, then we call a sequence zk a feasible sequence approaching point x if the following condition holds. For sufficiently large k, the sequence zk will be inside of omega. And the second condition is that the limit of zk must be x. Okay, so this will be a feasible sequence approaching x. And with this feasible sequence approaching to x, then we can give the tangent direction. Okay, so what is tangent direction? It is defined as following. So we make this vector d to be a tangent or a tangent vector to a set omega at point x if the following condition holds. The first condition is that we can find a feasible sequence zk approaching this point x. The second condition is that there is a sequence of positive scalars tk with tk approaching to 0 such that the following condition holds, meaning that the limit of this ratio is exactly the direction d. Then we will call that this d is a tangent vector to the set omega at point x. Okay? And all the tangent vectors, they will make up the tangent cone to omega set at point x. Okay, so this is the definition for tangent cone. In other words, the tangent vector is defined as a limiting direction which is approaching to x. All right? And if we take a look at this limit, then it actually means that we got a feasible sequence approaching x. This is the first one. Secondly, we also got a sequence of scalar tk approaching 0 to make this limit exist. And the limit will be the tangent vector. We give an example in the next page. Now, in this page, we actually have the feasible region as a circle, okay? A circle. And we consider the tangent cone at the non-optimal point minus square root 2, 0, this point, okay? Right here. And let's construct two sequences to derive the tangent vector. So one sequence is the zk like this. So we take it from downward to x, okay? And it moves along the direction of zk here and approaching to the point x in this way, okay? So as k goes to infinity, zk will approaches x. And we make the scalar tk as the distance between zk and x. Okay, so by taking the limit, then we can get the limit direction d as 0, minus 1, this direction, okay? Because we are approaching this x from downward. Similarly, if we are approaching x from upward, then we can similarly get another direction, tangent direction as 0, 1, 0, okay? Now, the tangent cone will make up by the two vectors here, right? So the first component is 0, and the second one is actually both negative or positive or 0. Okay, so this meaning that the second component here is actually free to move any direction. Now, having given the tangent cone, you can see that actually tangent cone is not easy to calculate, okay? Given you a non-optimal point, calculating the tangent cone may be very difficult. And to that end, we need to use some alternative way to represent this tangent cone. The alternative way is actually called the linearized feasible direction, which we actually used in previous parts. Now let's recall our constraint is some equality 1 and inequality 1. And also we have definitions for the active set, which actually means those constraints that makes strictly equality constraints, okay, at some point x. Now, having the constraint and active set, we can define the linearized feasible direction in the following way. So this set f at the point x is made up of those directions. So such directions have to satisfy two conditions. The first one is for all equality constraints, this direction must orthogonal to the gradient of these constraints. And for the inequality constraints and also active constraints, the inner product of the direction with the gradient of constraints must be greater than or equal to 0, okay? Which means that in this set, we actually contain some linearized feasible direction, okay? And also notice that in this linearized feasible direction, this set is also a cone, because if you multiply it by its positive scalar, it is still a feasible set in this set, okay? Now, let's take a look at how we calculate the linearized feasible direction still for the constraint here, okay? So at point here, and let's calculate the linearized feasible direction. Recall that the definition for this case is that we only require the direction is orthogonal to the gradient of equality constraints, okay? So if we take the gradient of equality constraints, then we can get the following condition. By taking it to be 0, we can see that it actually means that D1 is 0. In other words, the linearized feasible direction also takes the form as the first component to be 0 and the second one is freedom. So compared to the tangent cone we analyzed before, you can see that the two sets are actually the same. In other words, sometimes or under some conditions, the linearized feasible direction is exactly the tangent cone at the same point. So you may ask, under what condition the conclusion will hold? Okay? So this actually brings the constraint qualifications. And now let's give a very special class of constraint qualifications, which is LICQ. It actually means that the linearly independent constraint qualification. The definition is like this. Assume that we have a point X and we got the corresponding active set for some constraints, right? Then we say that the linear independent constraint qualification holds if for all the active constraint gradients, they are linearly independent. Okay, so if this condition is satisfied, then we say that LICQ holds. Now we have some remarks about the LICQ property. So as we mentioned before, that the tangent cone and the linearized feasible direction may sometimes coincide with each other. Okay, so under what condition they will coincide? So we need some constraint qualifications. And we can see that, or we can prove that under LICQ condition, then the linearized feasible direction does coincide with the tangent cone. So this is a very helpful property. Therefore, in our following optimality condition analysis, we will always use LICQ. Actually, there are also other constraint qualifications like the Mazarin-Formovitz constraint qualifications or other different types of constraint qualifications, under which we can also get different characterization about linearized feasible direction and the tangent cone. Also, LICQ is actually a very special constraint qualification, and under which we can have that the two sets, they are the same. Okay? So this is the main conclusion of this part. Now let's make a brief summary about this part. We basically introduce the constraint qualification, which actually plays an important role in analyzing the relations of linearized feasible direction as well as tangent cone. Okay, we stop here and see you next time.